Hi, I'm Julie Waldron, Research Fellow from the University of Nottingham. Today, I will be presenting a paper about decarbonizing our transport system. This paper is an outcome of the Project E-Velocity. 92% of the world's population lives in places where the pollution exceeds the recommended air quality levels. The major pollution sources include power generation, buildings, and transport. The transport sector alone is responsible for 20.5% of the global carbon emissions. As a result of COVID-19, air pollution levels have fallen to unprecedented levels. This pandemic effect on air pollution provided us with a glimpse of how a low-carbon future could look like. In order to reduce emissions, many countries decided to phase out fossil-fueled vehicles. The most ambitious plan is proposed by Norway in 2025, followed by many other countries in 2030. However, this transition will bring big challenges for cities, as we'll need to install charging infrastructure compatible with different types of users, we'll need to increase the generation of renewable energy, and we'll need to think in how to prevent energy shortages by using new technologies to balance the grid. In this research, we conducted a behavior analysis of a university fleet. We aimed to be able to assess the compatibility of the fleet with electric vehicles. We evaluated the charging infrastructure required, assessed the compatibility with vehicle-to-grid technology, and estimated the carbon emissions that we could reduce at the end. The sample was a fleet of 49 vehicles. The data was retrieved from a telematics system installed in the fleet. This provided details such as the locations of the vehicles and the time and duration of the journeys. The sample was split into 6 groups. 1 year of historical data was gathered for 5 groups and 6 months data for 1 group. This was due to data availability at the time of the research. These 2 tables present some details about the journeys made by the vehicles. The journey distance refers to the miles registered in a single trip, and the day distance refers to the miles traveled per vehicle in a day. You can see that the highest mean distance of a journey was 2.4 miles, and the highest mean in a day was 43 miles, which is around 70 kilometers. One of the most common barriers to make the transition to replace fossil-fueled vehicles by electric vehicles is known as range anxiety. This is a combination of feeling stressed by the possibility of the battery running low and the situation when the driver needs to travel long distances. Assuming a maximum day distance of 100 miles, it was observed that 99.8% of the time the vehicles from fleet 1 to 5 would perfectly fit in the range capacity of an electric vehicle. It was analyzed the stationary time, which provides a view of the probability of the fleets to be parking at a specific time. In this graph, each line represents a fleet. 100% means that all the vehicles were stationary, and 0% would mean that all the vehicles were in use. You can see that fleet number 6, which is the gray line, was active 24 hours. The other fleets remained stationary during nighttime and at lunchtime. The parking location analysis aimed to identify the main parking site of the fleets. The average likelihood of the fleets of being at different locations was calculated by analyzing the postcode registered at the end of each journey. This graph presents the results obtained for Fleet 2. The blue and gray line correspond to the most common parking sites of these vehicles. In addition, it is possible to estimate that most of them return to these locations during lunchtime. The simultaneous use analysis aimed to identify the behavior patterns of the vehicles and the most active hours of the fleets. The color represents the number of vehicles used simultaneously per minute. White means that none of the vehicles were in use, and red that all the vehicles were in use. The vertical axis corresponds to the months of the year, and the horizontal axis refers to a 24 hours period. For example, Fleet 1 does not have a specific start and end time, while Fleet 2 has a sharp starting time at around 7:30 in the morning and is finishing activities at 5 p.m. As previously mentioned, Fleet 6 operates 24/7. Vehicle-to-grid, or V2G, refers to using the bidirectional capacity of electric vehicles to store energy and sell it to the grid on demand. Fleet 1 to 5 were identified as good candidates for V2G due to the long stationary times during the night time, and also that they were stationary at the main parking site during midday, which would allow storage of renewable energy from photovoltaics. Finally, it was analyzed the CO2 emissions of one diesel vehicle and compared with an electric vehicle. It was estimated that an electric vehicle could reduce up to 80% the current CO2 emissions of the fleet. Thanks for listening to this presentation. Please follow us on social media and get in touch if you want to know more about the project.